In lesson 5-6, we're going to answer the question, how do I use algebra tiles and diagrams to model and identify equivalent expressions? So first let's talk about what equivalent expressions are. If you look at workbook page 183, you see some examples of equivalent expressions. Equivalent, you know, means equal to. So if we have equivalent expressions, we're talking about expressions that are equal to each other or that are worth the same value. So take a look at, the first example here. A plus 2 plus 3 and A plus 5. Those are equivalent expressions. You have A plus 2 plus 3, or you could write it as A plus 5 because you could combine the 2 and the 3 to get your 5. So that's what makes those equivalent expressions. However, A plus 5 and 3 plus 4 are not equivalent expressions. I don't know what A is. Because I don't know what A is, this is only going to work if A is 2. Right? If A was 2, then 2 plus 5 would give you 7, and 3 plus 4 would give you 7, and that would work. But because we don't know what A is, we can't prove that A is worth 2, I can't say that they're equivalent expressions. As you learned in Unit 2, the multiplication symbol can be dropped as long as it's not between two numbers. So keep this in mind. 3C, well, that's the same as 3 times C. Those are equivalent expressions. AB, well, that's the same as A times B. Those are equivalent expressions. Or 4 times the sum of P and 6 could be written this way, just with the multiplication sign. Those are equivalent expressions. Let's do some more work with equivalent expressions where we have addition signs, multiplication signs, and maybe even ones without multiplication signs. Take a look at the first example. 3 identical packages weigh 1/5 gram each, and you can see a diagram there. You can see 3 boxes of 1/5. So you could write it with an addition sign. So it would look like this, 1/5 plus 1/5 plus another 5th. Or you could think to yourself, oh, that's repeated addition. If I have repeated addition, then I can use multiplication to simplify that. That could also be written as 3 times 1/5, which if you do 3 times 1/5, you're basically going to get 3/5. Example B, 3 identical packages weigh A grams each. So example B is very similar to example A, except our package weight we don't really know. We're using a variable to describe the unknown weight of each package. So we see A plus another A plus another A. So you can write it that way with addition. Or if you want to take that repeated addition, use multiplication instead. You have 3 packages of A grams each, that's 3 times A. Which, if you take out the multiplication sign, it's just 3A. You can put them right next to each other. I don't know what A is, so I can't actually do the multiplication. I'm just going to leave it like that. Number 1, 2 boxes hold B books each. So let's see, if I were to use addition for that, I'm going to write B plus B. 1 box of B plus another box of B. Or, because it's repeated addition, I could just make that 2 times B, because I have 2 B's there. I should put the multiplication sign in here, because this box is with the multiplication sign. So this would be the one that I'd put without the multiplication sign, 2B. Number 2, 4 bags hold C peaches each. So 4 bags. I'm going to make my diagram here. I'm going to need to break it up into 4 squares. 1, 2, 3, 4. And each one holds C peaches. So let's see, I could do C plus C plus C plus C if I want to do the repeated addition. Or instead of repeated addition, I can write it as 4 times C, or 4C if I want to eliminate the multiplication sign. Alright, you can do some on your own. Next I want to talk to you about algebra tiles. Algebra tiles are kind of cool. I like them because they help you to identify, what parts of your expression are the variables and what parts of your expression are just the numbers. We call those constants, the numbers that we know. So remember, variables, they stand for the unknown, the things that we don't know. And then we have the numbers, which of course we do know. If I give you the number 5, well, you know that's worth 5. So, for example, what if I were to write an expression like x plus 2. I can use my algebra tiles, I can use my algebra tiles, see if I can do, I guess I'm going to have to turn off that. Okay, I can use my algebra tiles to show x plus 2. There's my x plus 2 more. Oops. There we go. Now I've got it. X plus 2. I have a long algebra tile to represent the unknown, the x, and then I have 2 of those little algebra tiles to represent the things I do know, 2. I could say, oh, a box of pencils plus 2 more pencils. So, these are the 2 pencils that I know. I know for sure there's 2 pencils. And then I've got this box of pencils. I don't know how many are in that box, though. Are there 8? Are there 12? Are there 24? I don't know how big the box is. So that's why I have a variable there. What if I changed it and I said, you know what, instead of 1 box of pencils and then 2 more pencils, what if I said I actually have 3 boxes of pencils plus 2 more pencils? So I would write it like this. I have 1x plus another x plus another x. I have 3 x's plus 2 pencils that I know for sure. I could simplify that because that's repeated addition. I can make that 3x, and this is repeated addition plus 2. That could be representing 3 x's plus 2. 3 boxes of x pencils. Again, I don't know how many pencils are in each box, so that's why it's unknown. I know there's 3 boxes for sure. I just don't know how many pencils are in each box. Plus 2 more. Hopefully you're getting the idea, because now we're going to draw some. Take a look at workbook page 184. We're going to use algebra tiles to model expressions. So we're going to write the expression that you see from the model. Here you can see we have x plus another x plus another x plus another x plus 3 singles. So I can put that all together. I've got 4 x's here. So I can just write 4 times x. Again, I don't need the multiplication sign. And you can definitely write it with repeated addition if you want. It's just a really long expression that way. I like 4x. Plus the 3 more that we do know. So if I were to go back and say this is the pencils again, I've got 4 boxes of x pencils plus maybe 3 more pencils. Or it doesn't have to be pencils, it could be books. There's 4 containers of x books. Again, I don't know how many books are in each container. Plus maybe 3 more books. So those are the things that I know, the constants here, those numbers. What if we were to draw the algebra tiles and they give us the expression? The first one is x plus 6. This is in number 7. Now, you don't have to get real fancy. It doesn't have to be colorful and all that. But here's my x. I'm going to use a long algebra tile for that one because that's the unknown. Plus 6. 1, 2, 3, 4, 5, 6. There's my x plus 6. Maybe it is, I don't know, 1 box of whiteboards plus 6 more single whiteboards or something like that. Number 8, 4 x's plus 1. 1, 2, 3, 4 x's plus 1 more. So I have 4 x's, 4 unknowns. Maybe it's 4 bags of peaches. Remember the peaches? 4 bags of X peaches. I don't know how many peaches are in each bag. I just know there's 4 bags of them. And then maybe 1 extra peach fell out, so it's over here. Now we're going to make a quick drawing of algebra tiles to help you to explain why 5x minus x is not equivalent to 5. So remember how we talked about equivalent expressions? 5x minus x is not equal to 5. And let's see why that is that way. First I'm going to make this part, the 5x minus x. So here's 5x, 1, 2, 3, 4, 5. So there's my 5 x's. Maybe those x's stand for the unknown number of, I don't know, papers in a notepad. Okay, I've got 5 notepads. And there's an X number of papers attached to that notepad. Maybe it's 100, maybe it's 200, maybe it's 500, I don't know. So 5 notepads of X papers attached to each. And then I'm taking away an X. I'm taking away a whole notepad. So what does that leave me with? 5 X's minus an X now gives me 4 X's, 4 notepads of X papers each. That is why 5x minus x is not equal to 5. This 5 is actually talking about something we do know, like 5 papers, 5 single papers, whereas the x's represent the unknown, 5 numbers of pads, or 5 pads of unknown amount of paper. So 5x minus x is not equal to 5 because 5x minus x is actually equal to 4x. There we go. Okay, now in workbook page 185, we're also going to model expressions without using algebra tiles. You can, do other models. We saw these on the other page. Take a look at example 1. We have the expression 3a minus 3. So for example, here's our situation. There's 3 boxes that each contain A apples. Notice we're using apples for A. I kind of like to do that. I like to use something that begins with the first letter or with that variable, I guess. William takes 3 of the apples. So we've got 3 boxes of A apples, and then William takes 3 of those apples. He doesn't take the whole box. He doesn't take 3 boxes. He just takes 3 single apples. So here's our diagram. You can see that we have 3 boxes. Here's 1 box, here's 2 boxes, here's 3 boxes of A apples. And then William takes 3 of the apples. So if you look carefully, you can see that they just circled 3 of those teeny little red circles and crossed them off to show that William is just taking 3 single apples, not whole boxes of them. So here's some equivalent expressions. You have 3a minus 3. That's also the same as 2a plus a minus 3 because you've got 2 boxes of A apples, and then you've got this other box of apples over here, but you're taking away 3 singles from it. You could write it that way. Or maybe you want to write it this way. You've got 3 A's, A plus A plus A, right? 3 boxes of A apples, and then you're just subtracting 3 single apples. Non-equivalent expressions would look like this. 3a minus 3 is not equivalent to A, right? Example 2, consider the expression 4b minus b. Hannah has 4 stamp albums with B stamps each. She gives 1 album away. So here's 1 album with B stamps. Here's another album with B stamps. Here's our 3rd album of B stamps. Here's our 4th album of B stamps. That's our 4B. And then she's giving 1 whole album away. She's not just giving away a couple stamps. She's not giving away something that we know, how much we have of it. We're giving away a whole album of stamps. I don't know how many stamps are in that album. So I'm giving away a whole variable. I'm giving away B here. Some equivalent expressions might look like this. We have B plus B plus B plus B, and then we're taking a B away. Or maybe you want to do 4B minus 1B, which is pretty much the same as this. Remember, all variables have a coefficient in front. Oops, that looks awful, but you could just put the 1 in front of it. Or just simplify it. 4B minus another B means now we have 3 albums, 3 B's. Non-equivalent expressions, well, 4B is not equivalent to 4. So for each expression, describe a situation that makes and make a diagram. Then circle the equivalent expression. So let's see, 4 plus 3D. Let's see, D. I'm thinking donuts. So maybe oops, gotta get my pen ready. There are 4 single donuts plus 3 boxes of D donuts. So my diagram might look like this. I'm going to have 4 here, 4 single donuts. You can even draw 4 dots if you wanted, plus 3 D donuts. So this is what we know. We know there's 4 singles, and then we have these 3 boxes of D donuts. I don't know how many donuts are in each box. Are they 6? Is it half a dozen? Maybe it's a full dozen. Maybe it's 12 donuts there. I don't know. Let's circle the equivalent expressions that go along with that. Let's see, 7D. Nope, that's not going to be correct because I can't put the 4 with the 3 Ds. I don't know what those Ds are worth. Oh, this one works. 4 plus 2D plus D. Here's my 4. Here's 2 Ds and another D. Or even this one works. 4 plus D plus D plus D. There's that repeated addition. I have my 4 single donuts plus another box, plus another box, plus another box of the unknown number of D donuts. Number 13. Let's see. Eggplant. I had eggplant parmesan last night. It's probably on my head. I got food on the brain right now. 2E plus E. So let's see. 2 boxes of E eggplants were delivered. Another box of E eggplants came late. Notice I keep talking about boxes. That's because I've got 2 E's, which looks like this, 2 unknown number of eggplants in each box. But then another E gets, another box of eggplants gets delivered later. So now I have 2E plus another E, 2 boxes plus another box. I don't know how many eggplants are in each box. I have no idea how big these boxes are. So that's why I have 3 E's. I've got all these unknown number of eggplants in each box. I just know there's 3 boxes. And let's see, equivalent expressions. This works. E plus E, because that represents your 2 E's. And then the other E that gets added later. So that expression would work. The second expression, no, that wouldn't work because remember, we need 3 E's. This 2 is supposed to represent, what we do know, and there's nothing here that we know. We don't know if there's 2 single eggplants anywhere. It looks like they're all boxes of eggplants, so that one won't work. But 3 E's work. We have, remember, 2 boxes of E plus another E. Now we have 3 boxes of E eggplants. Okay, so let's make a diagram for each situation and write 2 equivalent expressions for the total. There were 200 children already at summer camp. Then 3 buses arrived with G children each. So let's see, 200 children. Here's my 200 children. I'm definitely not going to make 200 dots there. And then 3 buses arrived with G children in each. I have no idea how many kids are on each bus. So the G is going to be for the unknown number of children on each bus. This is bus 1, bus 2, bus 3, 3 buses, G children on each. So let's see, I could write 200 plus 3G, right? 200 kids at camp plus 3 buses of G children. Or maybe I'll break it up a little bit and use some repeated addition, 200 plus G plus G, plus G. Could write it that way. You get the idea. You want to come up with your own equivalent expressions for the same diagram. Alright, write an equivalent expression with fewer terms if possible. Make quick drawings or use tiles if you need to. So take a look at number 22. I see 2 terms. I see 6 M's minus an M. I could use drawings or algebra tiles. I might use algebra tiles here. 6M. 1, 2, 3, 4, 5, 6. I'm getting a little lazy. I'm just using lines for the variables. So I have 6 variables, 6 M's, and then I'm taking an M away. So I'm going to cross one of those M's off. That means 6 M's minus an M actually gives me 5 M's. Now I only have 1 term. So all I've done is I've taken the 6 M's, subtracted out the M, and that leaves me with 1 term of 5 M's. 2 terms down to 1 term. Number 23, 8 1, 2, 3, 4, 5, 6, 7, 8, plus 3t. 1, 2, 3 t's. I don't think I can do anything with these. I can't put these with these because these are unknown. These are t's technically. And these are my constants. These are my numbers that I do know. I don't think I can simplify this one. Can't be rewritten. Okay, finally, our takeaways. So equivalent expressions are expressions that always have the same value. And remember, you can use algebra tiles and drawing diagrams. They can help you to identify equivalent expressions and understand why some expressions are even not equivalent, right? You can probably see which ones are equivalent and which ones wouldn't be equivalent. And remember, the long algebra tile, the green one, is your variable, the unknown, and then the little tan colored square, that's the numbers, or the things that we know.